Sorry, I was just trying to calm my nerves. This tech stuff is a little... I'm a digital immigrant, let's put it that way. Have you ever wondered how cell membrane proteins help regulate chemical traffic? Neither had I when I was your age. But here's a picture of a cell membrane protein maybe, and see a chute down there in the middle of it, the hole. That's going to regulate regulate chemical traffic. Screwed that one up. Here's chapter 7. Chapter 7 is broken down into 5 sections. The very first section talks about what cell membranes are made up of. Now, there's a big component of the first section that's all this experimental stuff. I'm not so interested in you learning about that, to be honest. Look at the eBoard site and it will tell you which sections to make sure to read, which pages to read in section 7.1. But if you look at it, this suggests that it's a pretty important chapter to the College Board, because all of these are being represented, and it's important for CMC as well. We need to look at all the sections here in chapter 7. Cellular membranes are fluid mosaics of lipids and proteins. What that means is that a cell membrane is basically made up of lipid. This is fat. This is canola oil. It's a unsaturated phospholipid mixture, and it's liquid at room temperature. This guy also is made up of fats, phospholipids, but it's made up of saturated phospholipids, and therefore it's hard at room temperature. All of your membranes that make up all cells in your body are a mixture of these two things, of both saturated and unsaturated fatty acids. So you have a little bit of hard and a little bit of soft, excuse me, at, God bless me, at 98.6 degrees Fahrenheit. I would like to think that something so important as a cell membrane is a little bit stronger than just this liquid, and that's why I got this bag out here. When I was growing up and I was a biology student, I was like, oh gosh, these things have to be super strong, but they really aren't. They're just bags made of fat, which is kind of interesting. You can see here that water surrounds both sides of a membrane. We live in an aqueous environment, meaning even inside of our bodies and inside of cells, the cytoplasm is also made of mostly water. You can see that there's a hydrophilic head to each phospholipid, as represented here by these guys, and a hydrophobic tail. This doesn't like water, and therefore it's oriented away from water. You can see also that there are proteins that are embedded within the cell membrane, and just like that first picture showed you, some of them will allow chemical traffic to go in and out, and they are oriented as well, that their hydrophilic regions are pointed to the outside and inside of the cell, and the nonpolar or water-hating regions of that protein is oriented on the inside, and that's usually due to it's oriented that way because certain amino acids like water and certain amino acids don't, so they fold in a certain way. We've evolved to have them either on the outside or hidden from water as a result of this. This allows then something called selective permeability, and you'll see that term in the first paragraph or two of the section. All it refers to is that some things can be let in and some things cannot. You'll also see a term called a fluid mosaic model. Fluid meaning they want you to understand that the things are always moving in the cell membrane. Excuse me. It's always dynamic. The cell membrane is pinching and poking out, and these proteins are moving around within it. And a mosaic means a variety of things that have come together to create something. So we've got carbohydrates and phospholipids and proteins and all sorts of things that we're going to get into that have come together. So that's a fluid mosaic, and this is a model of the cell membrane. Understand here when you see this that not only do the phospholipids move in 10 to the 7, that's 10 million times per second. What that means is that the phospholipids in here, let's say if this was a single layer of phospholipids made up of this, just like you see on the slide, those things can move back and forth and switch places super quickly. It's a very fluid process. I don't want you to ever think of a cell membrane as being this rigid thing like a table or a wall. It's not that at all. It's completely movable. Additionally, the phospholipids can flip, and you see that can happen once per month. Depending on if you have more saturated or unsaturated phospholipids, your membrane will be more viscous or more fluid. Viscous means kind of thick. I think of it as like tar. A liquid that's viscous doesn't really move that well. Cholesterol is something that's going to help give the membrane stability and rigidity, and that's okay. You need some cholesterol, but too much cholesterol will cause the membrane to be too stable or too rigid, and then it won't be able to phagocytize like we talked about in the last section. Additionally, you can see here that you are what you eat. The more animal products you eat, the more saturated fatty acids you will get, and the more viscous your plasma membranes will become, and the less able they will be to do their job. Now, I'm not a vegetarian, but I think about it every time I eat an animal-based product, such as dairy or meat or things like that.
Phospholipids contain a head group, choline in this case, that is attached via phosphate group to a 3-carbon glycerol backbone. 2 fatty acid tails are attached to the remaining 2 carbons of the glycerol. The head groups and the phosphate are polar, that is, they prefer to be in an aqueous environment.
Thanks for your help with that.
In contrast, the fatty acid tails are hydrophobic, that is, they are repelled from water. The fatty acid tails on phospholipids can be saturated with no double bonds, or unsaturated with 1 or more double bonds. The double bonds are usually in the cis configuration, which introduces sharp kinks. When forming a bilayer, unsaturated fatty acid tails pack loosely, which allows the bilayer to remain fluid. If there were no double bonds, bilayers would solidify to a consistency resembling bacon grease. Cholesterol is another lipid component of most cell membranes. It has a hydroxyl group, a tiny polar head group, so to speak, attached to a rigid hydrophobic tail. Cholesterol can fill gaps between phospholipids and thus stabilizes the bilayer. In a lipid bilayer, lipids arrange themselves so that their polar head groups are exposed to water, and their hydrophobic tails are sandwiched in the middle.
Pretty exciting stuff. Make sure you press pause and answer these questions. We will look at them in class tomorrow. Here's the first one. And here is the second one. Here are some objectives that I'd like you to also answer for class tomorrow. Take a moment to pause here and try to answer these. We'll talk about them in the morning. But 7.1 continues. It was just so long that I divided it in 2. I hope you're doing better than this feller is